Deep within the earliest chapters of cosmic history, there lurks a monster that defies every known rule. It is a celestial giant that, by all logical rights, should simply not be there at all. According to the standard laws governing our reality, the universe hadn't existed long enough to build it. Concealed within a primordial galaxy known as UHZ1, this anomaly has shattered our timeline of cosmic evolution. It was unveiled by the combined might of the James Webb Space Telescope and Chandra X-ray Observatory. It resides over 13 billion light-years away, appearing as it did when the cosmos was remarkably young. See this era, when the first galaxies found their shape and stars ignited their inaugural fires. Somehow, within that blink of cosmic time, this singularity ballooned to 100 million times solar mass. Based on every simulation of stellar death, a titan of this magnitude should not have been born. So we are left with a terrifying question. How did telescopes locate a monster breaking fundamental laws? Our narrative begins with the Chandra X-ray Observatory, meticulously sweeping a specific sector of the deep void. This window into the deep universe covers roughly 10 times the size of a full moon tonight. Throughout its long, vigilant watch, Chandra cataloged over 4,000 sources of X-ray radiation in this zone. Hidden within that extensive list was a phantom population that defied all our standard astronomical classification systems. These anomalies were blazing bright in X-ray wavelengths, signaling superheated gas and immense power hidden in darkness. When scientists tried to find them using optical telescopes, the locations were empty, creating a true ghost. When the James Webb Space Telescope opened its golden eye, researchers turned it toward these elusive dropouts. Webb's sensitivity to infrared light is unrivaled, granting the ability to perceive heat signatures previous instruments missed. When Webb focused its sensors on the target, the ghost finally materialized as a minuscule crimson dot. Spectroscopic analysis clocked its redshift at nearly 4, meaning photons traveled for 13 billion years to us. The galaxy hosting this anomaly was hiding behind a colossal foreground structure called the Abell Galaxy Cluster. Under normal circumstances, this alignment blocks our view. But here the cluster served as a cosmic lens. Over 2 weeks of staring, the data showed superheated gas screaming in X-rays, indicating prodigious energy release. This is the telltale heartbeat of matter, spiraling into a supermassive black hole and roasting to millions. When the team crunched the numbers, they arrived at a realization that shocked the entire scientific community. The central black hole boasted a mass equivalent to the total mass of stars in the galaxy. In our modern neighborhood of the universe, such a ratio is absurd and completely defies existing models. Take the Milky Way, where our central black hole is a tiny fraction of the stellar total. But in this ancient system, the monster and its host are equals, which is entirely backward physics. To grasp why this breaks our models, we must look at the speed limits of cosmic feeding. There's a theoretical speed limit to this feeding frenzy, known to physicists as the Eddington Limit. If a black hole began as a stellar remnant, it would need 1 billion years to grow. But the universe is only 650 million years old, so the math refuses to balance. This brings us to the core paradox. Either our physics is flawed or this hole started big. Enter the heavy seed theory, positing that some early black holes bypassed the star stage of evolution. Instead, they were born from the direct collapse of colossal gas clouds, holding thousands of solar masses. These direct collapse black holes would enter the universe, weighing 100,000 times the Sun immediately. However, the recipe for a direct collapse is incredibly fussy. because gas clouds naturally want to fragment. Usually as gas cools, it breaks into clumps and those clumps become stars rather than a hole. To get a giant black hole, you must destroy the molecular hydrogen using intense ultraviolet radiation blasts. Nearby stars pump out intense radiation that wipes out the cooling molecules and prevents the gas fragmentation. The gas stays hot cooling together until gravity wins, causing a catastrophic collapse. This merger creates what researchers call an outsized black hole galaxy, or OBG, pioneered by Priyamvada Natarajan. Not a region predicted. The black hole mass would rival the mass of the galaxy's stars, creating perfect parity. That is precisely the signature of UHZ1, where the monster and the cradle are growing in lockstep. If this holds true, nature has shown us a shortcut to building monsters. In the early universe, star formation seems paused. The galaxy is quiet, while the singularity feasts on everything around it. Spectroscopic data from Webb's near-spec instrument offers more clues, showing emission lines for hydrogen and sulfur. The width of these specific lines tells us how fast gas orbits the central black hole. The gas in this region is highly turbulent, and we detect a strong blue shifted signal there. Gas is rushing toward us at 540 kilometers per second, and this is a powerful outflow. This outflow isn't just local, it is galactic, with hydrogen gas glowing kiloparsecs away from the center. The winds from the black hole have traveled 3,000 parsecs north and 7,000 parsecs south. The speed of this distant gas matches the central storm, proving the black hole is blowing wind. It blows a wind that reaches the galaxy's edge, and the mass of this flowing gas is huge. The rate of ejection is about 3 solar masses per year, roughly the same rate it eats. For every single bite it takes, it spits a bite back out in a violent feedback loop. If we take the wind speed and distance traveled, we get a timescale of 12 million years. This fits well with how long we think these feeding phases last, so now do the math. If 100 solar mass light seed grew at the speed limit for 12 million years, it fails. It would only reach about 600,000 solar masses, nowhere near the 40 million we observe. To bridge that gap with a light seed, you need to break the speed limit by 10 continuously. That is physically unlikely. However, start with a 10,000 solar mass heavy seed and run the numbers. Grow that at the speed limit for 12 million years, and you easily hit 16 million masses. Push it slightly faster and you easily hit 40 million. The heavy seed model fits the data. There is another angle called episodic growth. Perhaps the black hole didn't feed continuously, but binged instead in that case. The total time needed is longer, but the active-on phases were brief. The implications of UHZ1 ripple across cosmology. If heavy seeds are possible, they solve giant quasar riddles. Trying to build those giants from small stars is like trying to empty the ocean with a teaspoon. But if you start with heavy seeds, the task becomes manageable because a large seed needs less growth. 100,000 solar mass seed only needs to grow 10,000-fold, not 10 million-fold. The outsized black hole galaxy phase might be a standard milestone in galactic puberty, where the whole dominates, then the galaxy catches up as stars form, eventually leading to the glorious equilibrium we see today. Z1 provides a crucial data point in this chaotic timeline. So, astronomers looked at its specific neighborhood. Using density mapping, they checked it. If it lived in a crowded city of galaxies expecting a cluster, surprisingly, HZ1 seems to be in a standard slightly dense suburb, not a massive galactic cluster environment. This challenges some theories that heavy seeds need crowded environments to form, but our maps remain incomplete. Faint neighbors might be hiding in the dark, or conversely, isolation might help get a direct collapse started. You need a pristine satellite halo blasted by radiation. That geometry might be easier in less chaotic regions. Delicate gas clouds aren't ripped apart by gravity there. And we are drawing maps of a shoreline never visited. We must play devil's advocate and ask, could HZ1 be just a normal galaxy with a standard black hole? It might be eating somehow way faster than we think possible, an extreme outlier of super Eddington feeding. Or maybe we are overestimating the mass of the geometry of the gas. Yet even if we lower the mass estimate, it remains uncomfortably large for its age, the theory holds. The heavy seed theory remains the most robust fit, but could it be a merger of two smaller galaxies? Unlikely, because the object is too compact. Mergers are messy and sprawled out, while HZ1 is a tight knot. The investigation is far from finished. The Discovery team has secured more time on Webb to stare deeper. They want to find oxygen-3 emissions, a tracer for ionized gas to map the outflows with precision. They also need deeper X-ray data to peer through the dust curtain and are hunting for siblings. They are hunting for other outsized black hole galaxies, hidden in archives if HZ1 is one of many. It changes everything. It means the early universe was a factory for heavy seeds, and Webb is hunting now. Webb has been hunting for over 2 years now, finding hundreds of active nuclei at high redshifts. We see a universe that was more active, violent, and accelerated than we ever dared to imagine before. Galaxies matured faster, black holes gorged themselves sooner, and star formation happened in places we thought impossible. And HZ1 is the poster child for this new wilder cosmos, and it forces us to completely rewrite the textbooks. We build models, we test them, and when the universe throws a curveball like HZ1, we must adapt. They magnify the faint and stretch the small, letting us see the unseeable. But they introduce complexity. Reconstructing the true image from a warped lens is exactly like solving a puzzle in a funhouse mirror. Yet the model for Able 2744 is solid, giving us confidence in findings. Another oddity is the dust. HZ1 is filled with it, and it is shockingly hot. And where did it come from so early? In the early universe, there had not yet been enough stellar generations to produce this much heavy material. The black hole wind itself might be manufacturing dust, forging it in dense outflows, and HZ1 is not alone. Z1 is different because it is faint, and it represents the silent majority of black holes we usually miss. Webb is uncovering little red dots, compact, dust-shrouded objects that might be the missing link in evolution. Z1, with its verified X-ray signal, is the Rosetta Stone for deciphering these dots, so we return to the start, a black hole defying the calendar. An object too big for its britches. Tells us that the primordial universe was a realm of extremes. Our previous models were safe estimates. The reality is far more dramatic, and the discovery of HZ1 proves that we are still novices here. We have mapped the gross structure, But the intricate machinery of cosmic creation is still being revealed. Today, every observation is a piece of the puzzle. Sometimes pieces fit, sometimes they demand that we build bigger tables. Webb is just getting started, and for now, UHZ-1 stands as a monument to the impossible. A paradox exists defying expectations, urging us to look closer. If you want to keep exploring these cosmic anomalies, make sure to hit that like button and subscribe to Wines of Thought that we just scratched the surface. Do you think these impossible black holes are common? Or is UHZ-1 just a rare cosmic glitch?